This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hello everyone, so welcome to another lecture of construction history. Today we'll talk about Gothic cathedrals. It is a logical continuation from our last discussion on Byzantine architecture and Romanesque. There is continuity, but of course there is fundamental differences. Now we will talk mainly about the Gothic cathedrals that developed primarily in France, and we will talk about the early Gothic stages, so the medieval original Gothics, not necessarily the Neo-Gothic, and the proliferation of revivals that characterized much architecture until the late 1800s at least. And I will also, as I said, focus primarily on France, but you should be aware that Gothic obviously had an enormous fortune also in Middle Ages, in the medieval times, also in England, in Germany, in Italy, in Spain, and so forth, with very important also regional variations. Now we will start introducing another type of arch. We already discovered the arch, particularly through the Romans, and then we saw how it continued in Byzantine and in the Romanesque building. But the Gothic architecture is mostly known for the pointed arch. Now, in order to understand the pointed arch, we have to compare it with the semicircular arch, which is the one we are already familiar with. And now, the semicircular arch, we already mentioned some of its key principles. We also said that there are some fundamental terms to remember, like the keystone here at the top, the voussoirs, which are all these stones that are generally trapezoidally shaped, and that are connecting the key, and they're taking the loads of the keys down to the springing point or abutment, at the sides, on both sides. Now, an arch works with a very simple but also very delicate principle. It works only in compression. So, in other words, it works on the assumption that each one of these voussoirs is not able to slip and is transferring its load progressively. It's obviously subject to a gravity, but it transfers the gravity laterally to all the voussoirs. So what happens in essence is that these compressive loads tend to transfer themselves and eventually result into a discharge on the sides, which, depending on the configuration of the arch may have two components of discharge of the loads. So one is the vertical load and one is the horizontal load. And obviously, this configuration may change. If you were to understand an arch, you could imagine a chain that is being subject to simply gravity. So if you would reverse the shape of that chain, you will find a natural shape through which compressive forces would travel. Now, the semicircular arch is not necessarily a natural curve that will result in the distribution of gravity, but it is a practical shape that it's very easy to set. So, like anything that is circular, it just requires a fixed point and an ability to rotate constant length. And in this process, it is, as we saw, possible to create centerings and geometries that derive from this, like the barra vault, the groin vaults, and so on. Now, as we said, the problem with the arch is that it has this lateral thrust. And so if an arch was to be built without any restraints at the point, it would inevitably tend to spread sidewise, like in this fashion, and it will collapse. Okay, so normally what we find is arches are restrained, and what they tend to do is more or less this. Obviously, this has been exaggerated, but they tend to transform themselves like as a structure that is known as an arch with 3 hinges. So they tend to rotate at the abutments, and they also tend to rotate at the key. Now, an arch with 3 hinges, now obviously this is an exaggeration. The arches would tend to keep their shape more or less in a way that you would recognize it as a semicircular arch. But the good news about this configuration, this is an isostatic structure that is stable. In other words, it's in balance, provided that the 2 sides of the arch have stresses that are within the limits of the structure, and provided that each one of the voussoirs is not slipping in relation to another by an amount that the arch loses its continuity. So this is something we discussed also, if you recall, when we introduced the problem of the lintel, where we said that stone lintels have a tendency to crack at the bottom, and in effect what they do, they too tend a bit to work like a structure that is hinged at 2 extremes, and it's also hinged in the middle. But these 3 hinges all together, they still maintain this structure in equilibrium. The problems arise when there might be another 4th point of hinging, so normally an arch at that point will fail. Now, this is an introduction. We're still talking about semicircular arches, but why the pointed arch? Why is it so important, and why is it the characteristic element of architecture and Gothic architecture? Well, the reason is because a pointed arch, first of all, it's defined along an axis of symmetry, and instead of being a continuous sweep at 180 degrees of like the semicircular arch, it is the combination of 2 segmental arches, or in other words, 2 portion of a full circle that are meeting along this central axis, and they are normally so they are both circular portions, but they are typically, like in this case, they sort of set up on center points that are about 1/3 of the actual span. So you take the span of the arch divided by 3, in the middle you might find 2 points that might be suitable for drawing a good pointed arch. That was often actually built in this way in Gothic architecture. But what is it really that makes it work more desirably than anything else? Is the fact that this configuration, in a certain sense, it acknowledges the fact that there is a point of rotation there. The 2 arches are not necessarily sort of supporting one another. So this arch, you would imagine it with a tendency to rotate here from left to right, but the other side of the arch would tend to do the same. So the 2 arches are almost supporting on each other at the key, number 1. But secondly, they discharge their loads, still working with gravity, but they do so in a way that has still a thrust, so a horizontal component of discharge and a vertical one, but the horizontal component is less than an equivalent semicircular arch. So in other words, the pointed arch tend to discharge its gravity loads in a way that it's more it has less tendency to burst than a normal semicircular arch would. But there are other very important characteristics about this, and we already saw some of the problems before when we spoke about groin vaults, and the fact that if you have semicircular surfaces, like they are cylindrical, when they meet in the middle, for example, in a configuration of a vault, they generate elliptical ribs. Now the pointed arch can be then applied to the context of a vault or a bay, for example, of a church or a cathedral. And what it does, it creates a situation when there's more flexibility about covering the space. So, first of all, so you imagine this to be the nave of a church, nave being the central aisle of a church or a cathedral. If you have an arch that is pointed on both sides, here, and you call because this is a transverse arch, which creates a transverse rib. Well, this arch can be set in the way we just described, so you can imagine to have two radiuses that define the two sides of the pointed arch. But on the other side, we're not restrained anymore to have a semicircular shape. We can simply raise up the springing point. Whereas here on a transverse rib we can start, for example, at this point. On the side aisle we can set up the arches facing the aisles to start at a higher level, and we can also not necessarily have the same curvature of the larger one. We can just simply dictate the control the apex of the arch, and then set up a curvature that might be there'll be some limitation in doing that, but there's certainly more freedom in order to reconcile the geometry so that they can all meet here at the crown. So there is an inherent advantage that is, yes, structural, but it's also practical in setting out the architecture. So there's another advantage that suddenly opens here. As we said when we spoke about groin vaults before, we said the groin vaults have elliptical ribs. If you have two groin vaults generated simply by semicircular surfaces. Now we don't have semicircular surfaces anymore. We have a series of pointed arches, but if we set up 4 pointed arches in order to create a vaulted bay, then this time we can still create a semicircular rib in two directions, and then draw or define the two or 4 pointed arches that can meet the same apex. So we can just set up two semicircular profile that cut across the diagonals of the bay, and then define 4 arches that will all meet here at the same point of the semicircular diagonals. So as you can see how this system is naturally taking us to understand Gothic now as a linear type of architecture and a construction system. So the nature of Gothic, like most of the construction system we inherited from the past, fundamentally they derive from the construction systems. They had an aesthetic appeal and control, but the Gothic approach was ultimately that one that created this ability to have a flexibility of setting up surfaces along lines which were known as ribs that define the vaulted space, particularly in cathedrals. But the same technique was also used in many civic buildings of the Middle Ages. So the pointed arch did not just define the religious architecture of Christianity in Western Europe. In fact, in itself, the pointed arch is actually of Eastern origin, but certainly it defined much more civic architecture for centuries to come. Now, before we proceed further, let me take you through some terms that might recur on this in this discussion here, in this discovery of the building methods of this period in time. Now, because we will use the cathedral as the example that prevails in order to understand the benefits and the characteristic of Gothic construction, let me take you through some fundamental terms. So now churches in plan are divided in typically in 3 or more aisles, of which the central one is known as the nave, and the side aisles are the ones that usually sit on each side of the nave. Now, Gothic architecture can be understood from top down, so we can start here from the top. We discussed the pointed vaults. At now the point where two pointed arches meet is still known as the keystone, but you have transverse ribs, which are the ribs that define the vault, and they are the arches that define the spacing and the span over the nave. And then you have wall ribs, which are the ones that lay on the orthogonal direction of the transverse ribs, and usually are the ones that frame up the clerestory, these very large areas glazed to allow sunlight inside the nave. Now all these forces from the vaults are then discharged into piers, over which normally there's an area known as the triforium, which is triforium defined again by pointed arches and usually 3 openings in between, hence the term triforium. On the outside, very often you'll find there's a system of buttresses that comes from the vault and then discharges, and we shall see some of the lateral loads of the vaults into by using flying buttresses, which are spanning from the side walls of the church into some external buttresses, connecting the two, often with an angle, sometimes more pronounced than other times, sometimes with segmental arch, sometimes with semi from a quarter of a circular arch, sometimes in tiers, sometimes bifurcated, so there's many variations. And then normally over these buttresses, but not all the times, there might be further decorations known as pinnacles, which are not just decorative, but they add more weight on top of the buttresses, and they help to, as we will see, to stabilize the structure altogether. So the structural principle of the vault, I think it is clear. Now that you know a pointed arch tends to discharge more vertically than a semicircular arch, the cathedral becomes that perfect architecture that anticipates the skeleton construction systems of modern times. This has been said many times. It is probably a bit of a cliche, but the Gothic cathedral are ultimately a structural expression that from which you can understand the transfer of loads. Not all the times. There are some tricks. There are some departures from this. And it is important to understand that Gothic builders didn't have the structural computational means of today, but they simply had an intuition and an understanding of these forces. We're still talking about structures that resist mostly compressive stresses, but in some cases these stresses can become also localized tensional stresses that can put some strain on this building. So generally speaking, cathedrals can be understood, as we said, from top down. We leave for the time being the roof, which is sitting further up, and when we just concentrate on these masonry vaults, normally done with small size stones. Now the vaults would discharge on the piers, as we said, using the pointed arches that define the transverse ribs and the wall ribs. And then these loads from the piers normally would be picked up by these flying buttresses that would just discharge further down towards the external buttresses. They are more like an external pier that normally follows it's aligned with the transverse ribs. And then the pinnacles on top of that add more weight, so that the weight of the buttress itself somehow, for whatever kind of lateral thrust may come, it adds more weight into this, and it somehow drives these forces all the way down in a way that it's, if not perfectly vertical, certainly still within the main section, at least 1/3 inboard from the edge of the buttress at the base. So now, obviously, this is the mechanism and the fundamental principles of Gothic cathedral buildings. Now, let's have a look a bit more closely what kind of variations, what kind of problems arise for building this ribbed form of architecture. And so the perfect place to understand this is to look at the vaults. Now, the vaults are generally masonry, so stone that could be cut to size. They're not necessarily bricks anymore. Of course, there are examples of bricks used in Gothic architecture too. But they are ribbed vaults defined by pointed arches, and so they imply that there is a position normally in the ceiling space where all these ribs convey and then transfer, as we said, the loads onto a pier. internally, and then externally they discharge alongside the buttresses and the flying arches. Now this does a very simple thing. It first of all it elevates the space of the nave. So you will, if you walk through some of these buildings, if you have been in any of these Gothic cathedrals, or you can even go into a neo-Gothic building here in Australia. That might give you a similar experience, but you will immediately recognize the sense of verticality and the fact that these buildings have very high ceilings and somehow dislocate or concentrate the structure in some points, freeing up some wall space to allow light in. Now this is obviously the architectural effect, but the means through which this happens is a very thorough control of masonry skills that inevitably have to convey forces in very concentrated spots. So a critical point that normally has to be addressed in any of these buildings is the springing point, where the transverse ribs, like this one here, and the diagonal ribs and also the side ribs sometimes, they all convey together. Now this is a building it's in Switzerland, that was restored by Viollet-le-Duc, a French architect who lived in the late 1700s and early 1800s, and is the master of neo-Gothic architecture. Viollet-le-Duc as well as restored many buildings, including this one here in Lausanne, and Viollet-le-Duc in one of his publications, he described this technique here with this beautiful drawing, explaining how all these stones are somehow sitting on top of one another, perfectly cut and worked out. And as you can see here, they tend to be fairly horizontal, but at some point they start to branch out. And so what Viollet-le-Duc is saying here is, in order to convey all these forces, you're building a bit of a micro stilt, one or two courses of stones that look like they are departing outside, but in reality they're still cut vertically. And then from some point on, all this nervatures start to depart and form the vault themselves. And this is what is known as the tas de charge. Now the advantage of a ribbed vault construction is one of the advantages, the fact that there is an ability to conceal very complex intersections between the different webs or surfaces that form the vault. So a ribbed construction, it's something we already met before, where we saw how the Romanesque buildings used to do that the same, very often using ribs of bricks rather than stone. But the intent was very often the same. It was that of creating a point of intersection that could accommodate some irregularities or imperfections of different courses coming together. The price to pay in order by eliminating the ribs would be to have an absolute geometrical control of joints, something that will come back in the future with stereotomy in the Renaissance times. But this would be what would be required in order to have a stone vault at the groin. Every single course has to turn from one surface of the vault to the next, and all the blocks, and particularly the blocks along the groins, have to be shaped with at least 7 faces that are perfectly cut, and they need to be meeting all the other courses around. So this implies a lot of work, and this is not to say that this is simple to achieve, of course, but certainly allows a bit more construction tolerance than the example on the right. And so in fact, this is an example of what would very likely happen behind the rib of a Gothic vault. So you must see there's a certain regularity of courses. There are set almost in a way that you might recognize as parallel. So there's a linear arrangement that would allow to lay blocks used for masons just to obviously work faster and without having to worry too much about all these intersections. And the rib, and then on the other side of the rib, you might have someone else, perhaps a different mason, working out similarly, still in horizontal courses, but not necessarily having to worry about where everything would have to meet, provided that there's some coherence, of course, of the surfaces. And then the rib will come and cover all this Now, the price to pay for this, as we said, would be to have a perfect stereometrical control of cutting stone, which was not probably available at the time. So rib vaults, as we said, started in Romanist times. There's been many arguments which one was the first pointed rib vault. For many years it was believed this building in England was the first one, was certainly one of the first ones, but generally speaking, the debate is probably still open, I suppose, but this is nonetheless a very interesting image that show you the intent here of having, these rib vaults that clearly, particularly once plastered, they conceal any imperfections. Now, the pointed vault, however, traditionally and most of the time, at least in the early Gothic, has in France, and the so-called, when we say early Gothic, by the way, the word Gothic, it's not what the medieval builders used to refer to. In fact, if anything, in Europe during those days, it was referred to as opus Franciginum, in Latin, which means the French style or the French type of work. So, however, the French Gothic in particular has defined two families of vaults that are pointed. And the first one is the so-called sexpartite vault, which is a vault divided in 6 bays, where you normally have two bays that are defined by the transverse ribs that are larger and defined by the diagonals, and then you have 2 smaller bays on the side. So overall you have here the 6 partitions of the bay. There is no rib that runs longitudinally along the nave of the church in the French Gothic traditional sexpartite vault. And so you can see here a representation of this vault with a diagram. Now the sexpartite vault is defined by the transverse ribs first, which span from pier to pier, typically with a springing point at the top of the pier, with some of the modifications we discussed, perhaps with the task, the charge, etc. But then the vault is defined by 2 diagonal ribs that normally are semicircular. So you can see how the vault is somehow defined first by the diagonals, and then the transverse ribs continue that. And then on the sides we have 2 smaller pointed arches that define the rest of the vault, which normally sit on a stilt, so they're elevated so that they keystones align with the crown of the vault. Now, a perfect example of this sexpartite vault, in fact there's more than one. This is the type of vault that was characteristic of the first generation, or the very first churches in particular that developed and cathedrals that developed in France towards the late 1100s and early 1200s. So you can recognize here a Bourge where you have obviously this is one of the bays, and the sexpartite vault generates also an intermediate pier, which could be treated sometimes to look like any other pier, but sometimes it's also treated as a different pier of a smaller size than the corner ones. And so here's the 6 webs of surfaces that define the vault. And here are some views of this wonderful cathedral, still extant and almost as it was built in those days. And you can see here the partitions in 6 parts. The other vault, however, that developed in France was the quadripartite vault. Now, all this might seem pretty pointless, but as we shall see, there are some important differences and some reason for which these cathedrals have evolved in the configurations of vaults. So the quadripartite vault, of course, as the name implies, is divided only in 4 webs. Again, it is defined by the transverse ribs and only by 1 wall rib on each side. Now the diagonal ribs are still semicircular, so that is maintained, the setting around coming from the diagonals is contained. And yes, there is still a need to elevate the wall ribs on the sides because they have obviously a lesser width from which they start from. Now, the Cathedral of Chartres is a perfect example of a quarter-partite vault. So you can see how there's a more frequent and rectangular kind of layout rather than a square layout that repeats itself. And again, this is some of the views of the famous Cathedral of Chartres. Again, another examples. They almost survives, almost untouched, apart from some minor alterations. And like many other buildings in Europe that they look Gothic today, but they were very often finished off or completed or altered significantly in a lot later than the 1100s or 1200s. Many Gothic cathedrals in Europe were finished in the 1500s, whereas at the times of the Renaissance, and many others were also altered significantly or restored in the 1800s in neo-Gothic fashion. And so here in Chartres you can see clearly the original kind of medieval Gothic, again with the transverse ribs now looking up, defining the spacing of the nave, the crown in the middle, the semicircular diagonal ribs, and then here you find the wall ribs that sort of frame up the clerestory and then come down through the triforium all the way down to the piers. Now, why this difference? So why did the French builders of the cathedrals suddenly change, or why did they choose one versus the other? Well, there's been debates about this, but one of the most convincing arguments, I think, is the one proposed by Robert Mark, which you'll find many readers, by the way, on LMS. And I believe Mark is correct when he says that one of the main reasons for which it is worth going from a six-partite vault system to a quarter-partite is simply a constructional matter. This because, yes, many has been said, there's more verticality, it sort of enhances the verticality of the space, etc. But the reality is that if you have a vault with a square bay, ultimately like what the sexpartite does, yes, because the sexpartite base has some piers in the middle, but the thrust that comes here is mostly along these four piers. And what happens here is that the component of this charge here from the vaults and from the diagonal ribs, which are the ones that pick up most of the loads, and they are the first one that are built, by the way. The component of lateral force here, it's something that could be picked up by the buttresses. But if you're building a cathedral, and normally you would go bay by bay, it's modular construction almost, in order to have, whereas you might build piers and have some side buttresses that will be able to absorb these thrust, the thrust from this side of the cathedral is not going to be absorbed until the next bay is built. So, for example, if this bay was built first, there would have been a time where the thrust coming from these diagonal ribs, particularly if the ceiling is very high, could have been such that a lot of props, a lot of temporary works to prevent this pier to collapse along this way until the next rib will come into place. There was this sort of temporary need to prop the structure. Whereas sideways, perhaps the problem could have been resolved by building first the buttresses and preventing the lateral load. So, normally you think that the cathedrals have to discharge horizontally, which is why they have all those flying buttresses. But when they are built, they also needing to be restrained in this direction, because once it's all built, each bay is counterbalancing the next bay. But before those bays are built, what's happening? And so this is a very interesting reasoning, because if you realize that if you start to have rectangular bays on the other hand, this diagonal rib will have a discharge that it's bigger in this direction, but it is smaller in the other direction. So if this is, you have to be precise when you draw these things, but this component of horizontal stress will be bigger on this axis than on the other axis. And it would be less than the one that will be developed by an equivalent square bay. So in other words, if I had here an equivalent square bay, it would be like this. This would require, a 45 degree sort of thrust that would have two components of equal size. But if I reduce it along this length, then I have halved the amount of side thrust that will have to be balanced by the next bay. So in other words, this is a dynamic sort of loading understanding that justifies why, and we will see how this has happened in history, progressively cathedrals moved from the six-partite to the quadripartite vault. But how were they built? Well, again, there's much debate, many discussions, many theories, some of which conjectural, some of which based on evidence of contemporary records, including plenty of representation that illustrated building works during the medieval times. So we're able to have an understanding of what kind of tools were available in medieval times. And it is no surprise to see that these are the tools of the masons that were already available in ancient times with some refinements. But we find there is some access to pulleys to lift up loads and capstans to use the principle of the lever in order to create more force for lifting up. We have axes, we have chisels, we have ladders, we have measuring tools like plumb bobs, we have mortar that is mixed on site and levels, and so on. We see other illustrations that describe, obviously you can see the chisel, the pickaxes, the manual labor involved, but also the mixing of material to create lime mortar. And yes, some plumb bobs, like in this case, some square rulers to measure and make sure the buildings are set. So we expect medieval builders to have good geometrical control. That was proved by what they've left, but also we know that they had availability of labor and quite a fairly advanced skill in creating false work. So in other words, in creating temporary structure for giving access to workers by having suspended platforms, what we would today call as high-rise gantries, methods of constructions that were able to allow access by using put logs or by penetrating the thickness of very imposing masonry structures by having timber scaffolds and ladders that are allowed to climb from the outside. We also have an understanding from pictures like this, which is a representation of building of the Tower of Babel, of course transposed into means and methods that would have been available at the time, by illustrating, for example, the use of a rotating crane. They need to handle materials like of smaller size that can be transported vertically, like bricks, small stones, and ingredients of mortar. And we do know also that they did use these systems because many medieval buildings have left these halls known as put logs halls that allow to run some timber members, often supported by vertical standards and horizontal ledges, for which some interwoven lath was used as an equivalent of today web forges of aluminium or temporary catwalks that were put in place for maintenance purposes or for construction purposes. We also know that they made plenty of use of treadmills. Now, treadmills were also understood and used many times by the Romans. In fact, this illustration here on the right is of Roman origin. It is a transposition by Durm, by Joseph Durm an inscription, a funerary inscription found in a tomb of a family of builders in Rome, the Ateri family. And you can see how in this expression here, there's this very frightening crowd of workers that are inside a rotating wheel, which is known as a treadmill. Now, this rotating wheel, with its motion, was able to operate a crane, and by being able to, with the use of multiple pulleys and stays, being able to lift up considerable loads. And the treadmills were used also in the Gothic cathedrals, very often at the top of the roof work, from which they were able to, the builders were able to lift up the heavier materials or the loads required for building masonry structures. This is a treadmill that still survives, for example, at the tower of the Salisbury Cathedral in UK. So the vault construction is often what is mostly known about the Gothic cathedrals, but we saw already before how obviously timber was an important ingredient of medieval construction. And certainly the roof of cathedral was arguably built first and before the cathedral. It was almost this approach where you can imagine that the builders were understanding the concept of locking out the building to protect also the works from the weather, and then finish off these intricate and very complex pointed vaults from inside by using the structure of the roof itself as a temporary platform from which to locate treadmills for lifting up works, and possibly also to suspend some temporary scaffolds. Now, you can imagine also how these pointed vaults needed to have some temporary works to support the set out and the forming of the vaults until they were completed. Now, as we said, the pointed vaults, and this is like most of the medieval vaults, including the Romanesque ones, they were often ribbed. And so ribbed vaults work on the mechanism for which you first build the ribs themselves and then you fill up the rest in between. So in order to do so, there would have been some frames set up first to support the ribs themselves. So you can see here in this representation, you might have had some half frames coming together, then joining under the ground, and these frames will be supporting the diagonal ribs in both directions. Then other frames and centerings would have been put in place to support the transverse and the wall ribs. Now, that was an example of a quadripartite vault, fairly square, although as we saw, the quadripartite vaults were very often more rectangular for the reasons we discussed. But the sexpartite vaults were also built with similar principles, where you would have had, again, 4 diagonal ribs, semicircular, built with half frames, and then further down, of course, on the sides, 2 more centering systems, very often supported with some scaffolding systems that connected back to, or that sprang from the piers and then allowed access straight under the vaults. And then, as we said, you would have had the ability to lower down materials by using perhaps treadmills from the top. And then false works that would have been set in place to shape these very convenient shapes of the pointed arch. So center points from which to set up and rotate arches and at their apex, and using a mix of options and of alternatives, of which perhaps these 2 on the sides could be understood as the bare minimum amount of material that would be required. So you would imagine that the medieval builders would have understood, at least from experience, how to minimize the resources and use the minimum amount of timber, a minimum amount of false work perhaps to achieve those incredible structures. Now, all this would have had to be completed by hung scaffolding that would, again, as we said, could have been very well perhaps straddling across these masonry piers, coming out at 45 degrees perhaps, or so, or less, or 60 degrees, and then creating a series of horizontal support points from which to create some temporary platforms. It should be expected that there would have been many, arguably perhaps many casualties involved in some of this construction. The safety requirements for that times would have been quite loose and certainly not to contemporary standards. But nonetheless, there would have been some systems of access that implied an elevated access for builders. And the illustrations, the representations we have for miniatures of the medieval times, they seem to imply that there would have been a need to climb up high in order to complete these structures. Now, most important would have been the use of centering again, particularly in the rib vaults that would have been perhaps using these systems of lagging, where you could imagine some fairly rough timber logs that would have been then cut to size and reused from one bay to the next, and then keyed together with the same system of centering we discussed earlier, where two of these frames will come together. They have a lifting block, a spacing block in between, possibly blocked again itself by some wedges that they will then remove. Then the block will come down and allow the two half frames to be lowered and moved somewhere else. It is imaginable that this would have been the approach, so almost like an early approach to engineered formwork, where some of the false work would have had to be reused several times, possibly, for reasons of continuity, but also for reasons of economy, because of the labor required in order to set up all these preliminary works. In between the ribs, it is possible there would have been similar arrangements of laggings, not necessarily boards cut in this way that somehow seem to imply that mechanical saws would have been available. This is the way you probably build a vault today, using boards that are coming on a longitudinal side, because it is easier to control a surface by having a series of points rather than connecting a series of planks. But it is most likely that this would have been probably a bit like the half frames we saw before. You would have had a log coming like that and another log coming together, probably with a curvature, with a block in between that might have allowed some spreading, some adjustments, and then this being tied together. So these surfaces are clearly a double curvature, so there's a curvature that is following the pointed arch in this way, but there is also a curvature that runs in this way, and there's also a camber very often at the top of the junction that makes things even more complex. So they're not necessarily a simple curvature that could be resolved along one line, and therefore there would have been some need for having some lagging that was adjustable. It has also been hypothesized that some of these vaults would have been built without any lagging, simply by relying on this very clever device of a stone-weighted rope that once tied to the scaffolds that would have come from the roof above, as we said, built before, then this rope, by simply being run past the latest of the course built, would have naturally induced some load, but having the resultant of the weight of the stone and the reaction you have from the rope in this direction would generate a force that runs in this direction, and therefore puts in compression the vault before it is completed. It's like a form of pre-stressing that it's happening during the construction system. Now, to conclude, I'll just take you just a little bit to go back on what we said before about the evolution of the cathedrals, but just simply discussing the case of the flying buttress. Now, we discussed mainly now how the vaults are defined, but the vaults themselves have a significant amount of thrust. There is normally a roof that sits above here, which we understand is a series of timber roof systems and rafters and trusses, perhaps sometimes in some cases. But the vaults themselves have a component of discharge of the weight. They are masonry structures that inevitably put a lot of horizontal thrust here in the structure. Now, the purpose of all this external structure you often see in Gothic cathedrals is exactly that of absorbing directly all these forces from the vaults and somehow bypassing these internal walls, so that these internal walls can be reduced in depth. They can allow more space to be glazed and therefore allow more light to come through. But also they allow to push further up vertically the crown of the vault, and therefore have this sense of verticality and grandeur that certainly define also the spirit of building the cathedrals. But all this external skeleton, it's built up to convey some of these thrusters back down to these external towers or piers of masonry, that, as we say, sometimes are pinnacles as well, but which with their weight they ultimately round and transfer all these forces down to the ground. Now, one thing to understand, these are very tall structures, and we'll see some dimensions to give us an idea of that. And therefore, they're not only resisting those vertical loads, they also are resisting the wind. So this is probably the first, one of the first cases in history where wind loads become understood and become also a very important determinant of the structural performance. So there are some studies, again, of Mark in particular, that I'll refer you to, that are very fascinating, that describe the performance of these cathedrals. And they also describe how in the 1970s, without having all the gizmos of computer analysis, very simply, some historians of in this discipline, they prepare some models of plexiglass that replicated the section of the towers, and then they loaded the scaled down models. They loaded these models, applied some scaling formulas to understand the implications of scales and stresses, and then analyzed how under stress some of these plastic models would refract light through them, therefore giving an optical analysis of the distribution of stresses. And so again, you will find some references where you can read these better, but you will find how Mark and others have demonstrated how these cathedrals react to the wind, and they do so by using these buttresses as a way to brace against the wind. In fact, in some languages, in Italian, the flying buttress is also known as contravento, or counter-wind device. So these are two sections that somehow represent close by this flying buttress approach. But the whole evolution of the Gothic cathedral can also be reconstructed through the buttressing. And so just you will find that this is mostly France, and it is over a period of 50 years where the earliest Gothic cathedrals were built in France. So the very original ones, and the ones that are probably the classic ones, if you wish, define that style. And so going quickly through them, you will recognize that the first ones, like Laon, one of the first ones, was a church that was still in transition from the Romanesque. So you have a central nave, about 23 meters tall. You have two aisles and two galleries on the side. And there is a clerestory here at the top. This is a Gothic building, but that allows some light from the top. In due course, you'll find that this building has been altered to also introduce some semi-quadrant buttresses, but this would have been the original configuration. The building has a sexpartite vault, so you have two diagonal ribs and an additional transversal rib also at midspan. And then Notre Dame de Paris, in one of its many variations of the building has been altered many times in history. This is a reconstruction of what the building could have been at some time during the Middle Ages. A taller structure, and that has probably one of the first time you start to see this very pronounced external flying buttresses, of which there are two tiers, one here at the top and one below, and even further ramifications of this in between. Now the building has two aisles on the sides and a central nave, and it was certainly a building that was subject to an experimentation level as it is now, but some of these initial buttresses can still be recognized in the structure that has been altered significantly. Still a sexport-type building, like Bourges as well. Now Bourges starts to take this concept of the flying buttresses to another level, and it does so with a very, very characteristic, almost triangular hut kind of configuration. It is still a sexport-type building, as we said. It's a bit taller than Notre Dame and much more taller than Laon, but it has this double bifurcated almost arrangement of the flying buttresses, and you can see here how the angle of slope is very pronounced. Now, one thing that Bourges did, unlike Notre Dame, it's that fact that it has, yes, also, in fact, in this case, three aisles really to look at it, but it sort of had the internal aisles to be taller than the external one, sort of creating this stepped configuration, from which you have a very, very tall clerestory, from which again much light will come through, and there's often some rationale here where the clerestory is high here, but these higher side aisles as well allow light to come through further, even to the most external aisles. And then Chartres, a magnificent example as well, but this is one of the first quadripartite cathedrals. Again, this is a representation of vaults. The roof is missing there, and you have, in this case, two, well, better still, three tiers of flying buttresses, two of which are connected by this array of columns. And the top ones, some have argued that perhaps were somehow not as efficient as the rest, because you can see how the vaults here will discharge at this point mostly, but some of them up here will discharge lower than the actual buttress. So unless this buttress was picking up something from the roof, it's debatable perhaps how they're not necessarily absorbing the thrust itself, but they are still providing, according to Mark, a stabilizing effect to the entire structure. Now the height of this nave is similar to the Bourges, but the building is much more compact. It only has two aisles on the side instead of this more triangular format of Bourges. And you can see how these buildings become bigger and bigger, and how the skill, particularly of this use of the buttresses, starts to lead to taller and taller as well. So it becomes 38 meters height here. Very clear recognition here of the two flying buttresses, and the buttress with the pinnacle, and this is Reims, which also incorporates a series of statues that somehow completes the external facade. And again, Amiens, probably one of the certainly still extant, one of the biggest cathedral, 42 meters. Again, similar in configuration to Reims, very tall buttresses completed by pinnacles, two rows of flying buttresses, and a very simple configuration. Absolute verticality inside, 42 meters, two aisles, and a very large space here, all three for allowing light inside the cathedral quite efficiently, so that any point of the structure there is, at some point of the year, the ability to receive natural light. And finally, Beauvais. Now, Beauvais is famous for its failures, but the initial vision was to have a cathedral this big, 48 meters tall. In this case, you have, yes, again, one nave and two aisles, but you have a configuration of flying buttresses that is also interrupted by a mid-pier there. Now, the cathedral collapsed in 1200. A quadripartite cathedral that was eventually rebuilt in part, which survives only a truncated part because the cathedral was subject to also further failures during its history. But this was probably the structural limit of that could have been achieved with the system of construction that probably didn't stand the test of time. And to conclude, I'll just take you through some of this. This building in Lausanne, in Switzerland, which is not necessarily in the same way as original as the ones we just showed, but it is a building that was founded and still has a good part of its structure coming from the early French Gothic, although Lausanne is in Switzerland, it's in the French side of Switzerland. At the time, Switzerland was not yet, and so here it's also interesting because we find how Viollet-le-Duc intervened to restore the building in the early 1800s, and you can recognize some of these features we discussed before at a smaller scale of the giant cathedrals of early French Gothic. You can now recognize here an interesting configuration here, the pointed arch, the side aisles that emits light from the walls, external walls, as well as from a clerestory on top. And you find here there's a six-partite configuration in this case, the transverse ribs meeting at the charge, and again here some views of the triforium here, sitting just below the clerestory, and you can see how the vaults here are clearly masonry construction of courses that are fairly regular, but then eventually are disappearing inside the ribs and correcting all the different irregularities that may apply from one rib to the other. And you can see how every vault, including the intersection of the nave and the transept, is always vaulted with ribs and all that. And then from outside, now you can see still the same structure, very simple, much smaller than the giant cathedrals of Amiens and Reims and Bourges and Chartres, certainly, but still, clearly this is the position of the ribs. These are the arches that define the flying ribs and the pinnacles and the buttresses that eventually help to reconvey all these loads down below. And again, a view from below, looking up. Now you can recognize clearly. Here's this quadripartite vault here, two transverse ribs, semicircular diagonal ribs, and so forth. So I'll conclude here. This is another step towards our discovery of construction systems, and hopefully also you're starting to understand how architectural styles also have evolved out of this construction system. So I'll leave you here, and I'll see you next time.